Hello, welcome to my first video. I am going to be talking about graphs, specifically node edge graphs. So, the example graph we're going to start with looks just like this. Right? We have 3 vertices and 3 edges between them. Okay? How we formalize this graph is we define our graph G, give it a name, and we define it in terms of a vertex set and an edge set. And then we define our vertex set and our edge set using labels. So our vertex set I will define as a series of 3 elements, v1, v2, and v3. And if I go back to this diagram, I can simply label it v1, v2, v3, in whichever order you prefer. Now, our edge set, I'm going to first use this cumbersome notation, which makes it very clear what the elements of this set are, and that is by listing it explicitly as a set of tuples. So, the first edge set, I will list like this, the edge connecting v1 and v2, then I will list the edge connecting v2 and v3, and then I will list the edge connecting v3 and v1, like so. Now, some equivalent notation that is convenient to use is instead we just remove the extra brackets around the tuples, and they're sort of implied, just like you're used to with your multiplication. Right? I will note them like this. Now, in the context that we are understanding here, we're looking at simple graphs. So in our case, this is actually the same as if I was to start changing the order of some of these. So if I keep those first 2 edges written in the same ordering, and I decide to write this one instead as v1, v3, nothing changes. Now, another notation you might sometimes see, if it's convenient, is instead of indicating which vertices are joined, you might just assign edge labelings like e1, e2, and e3. However, we'll avoid this for today. Now, let's talk about what makes this specific graph a simple graph. This graph in fact has a name, and its name is the complete graph on 3 letters, K3. It was a terrible 3. K3. Now, what makes this graph simple? I think of it in terms of what it doesn't have. It is not weighted, which means the edges do not have a corresponding weight associated with them, which will make more sense a little later. It's undirected. The undirectedness is what allowed us to make this equivalence right here. If we distinguish between these two, then we require direction. We do not have this. Help makes it simple. Now, we also don't have any loops. Loops are features which look like this. If I was to edit our previous graph, a loop looks like this. All right? And we do not have any such loops. Similarly, a directed edge would look like this, and a weighting you would denote with just a series of numbers, like maybe a 3 and a 2. Other features that our simple graph has, does not have any parallel edges. Parallel edges look like this. We also, a little more complicated, it's not a hypergraph, which means that each edge corresponds to 2 vertices. I'm just going to state that one. Don't think about it too much. You'll encounter hypergraphs much later on. They're not something we're interested in today. They are, however, very cool. Now, each of those special classes where we allow for those different things that I've said we can't have in a simple graph can be assigned a name. So there's not any name that I ever see used which means you have a simple graph with loops allowed. That's just normally stated that you allow loops. However, a directed graph, where we allow for these arrows, such as here, is frequently referred to as a digraph. If we allow for parallel edges, like here, it's frequently referred to as a multigraph. If we allow for a weight and direction, and we allow for parallel edges, I will frequently see this referred to as a network. Sometimes a network will also include something called capacity, which you can think of as being a second weighting. It's a little more nuanced, but for now, we don't need to worry about that. And the last one is a little cooler, which is the hypergraph. How the hypergraph works don't think about it too much, right, is instead of having an edge which simply connects two vertices, I'll color the edges here. This is one edge connecting those three vertices, and then we could have another edge connecting those three vertices, and that would be a hypergraph where we have edges in the middle. Things we don't have to worry about in our simple graphs for now as well. We're not really concerned with how we actually lay them out on the page. So, for example, if I was to take a graph with these vertices here, and I will copy these vertices one time, there we go, just like this. We would consider these two graphs to be the same regardless of how I actually draw the lines connecting these vertices. So if I draw it like this, right, that graph is the same as if I had bothered to avoid crossings. Let me make sure I don't miss any. I'll avoid that one crossing. Just like that. For our purposes, these two graphs are the same. There is an interesting context where you can consider how you draw the actual graph, in which case you're normally concerned with what I've kept calling crossings, which look like this. But we don't have to worry about this. Now, let's talk about some kinds of simple graphs. The first one I already mentioned is the completes. The complete graphs are a series where every vertex is connected to every other vertex. And I will draw out the first four for you in this sequence and trust that you can fill them out yourself. So, the first one we have on the end is not particularly interesting. It is K1. It's just an isolated vertex. We then have K2, where we have two vertices connected by a single edge. We then have K3, which I did before, and it looks like this triangle. And then, where we actually can begin to distinguish our complete graphs from other graphs is K4, the complete graph, which is not a square because we have to deal with these cross edges. Another kind of graph that you will frequently encounter is called a cycle graph. I'll draw out the series of cycle graphs up to C4. So once again, C1 is the same as K1. C2 is actually the same as K2. C3 is the same as K3. And the reason I mentioned that K4 looks different is because if I draw C4, I get that square. In the cycle graph, as you can see, we have a cycle, which means that we can continue to run around the graph just like that. And that's actually all the structure that there will be. So every vertex is only connected to two edges, and it's always connected. Another kind of graph, which is very useful to see, is a bipartite graph. Bipartite graphs contain two distinct vertex sets, which if you want, you can write your vertex set of a bipartite graph instead of how we did before. You might wish to write it like this, as the union of two disjoint vertex sets. And the reason for that is because when you draw your bipartite graph, we might have a vertex set here, which corresponds to V1, and we might have a different vertex set, might have the same number, might have a different number of vertices, which corresponds to V2. And then we view our vertices for the graph as the collection of both of these, or the union, right? Now, a bipartite graph, what distinguishes it aside from those two disjoint sets is the edges only ever travel to the opposite set. They never travel within its own set. So if I was to draw a bipartite graph, I can start from V1, I can go to V2, I can go to V2 however I like, I can go as many times as I like, and this is a bipartite graph. It's currently disconnected. We can join it up, maybe I add one here, maybe I add one here. This is a bipartite graph. One notation you might see used to try and visualize bipartite graphs looks like this, where I take two shapes, typically they're just ovals, and I will label this one V1, this one V2, and as you can see, our edges only travel across. There is nothing that looks like this. Now, That is bipartite graphs. We also have things like the complete bipartite graphs, which I'll just draw out a couple simple ones here. Quite easy to see. This first one here I'm going to draw is called K2, 2. Here I will draw K3, 3. In here I will draw K2, 3. And typically there is a little comma right there to distinguish it. Now, K2, 2 looks like this. It's the complete bipartite graph on 2 and 2 vertices. K3, 3 looks like this, and is the complete bipartite graph on 3 and 3 vertices. And as you can see, each vertex in one side of our bipartite graph is connected to each other vertex in the other side of our bipartite graph. K2, 3, similarly, just to show that the numbers need not be the same on both sides, looks instead like this. Right. Other kinds of simple graphs which you will be exposed to see, and one that is particularly useful, is called a tree. Now, if I have a tree, it looks like this. Right? Every vertex sort of flows down. This kind of looks like a factor diagram, if you remember drawing those out in primary school, right? You can have disjoint trees or disconnected trees as well. Similarly, you can have disconnected graphs as before. I neglected to state that explicitly, but I can either view this, right, as two separate trees, or I could also view it as one graph. In the case where it's two separate trees, there's a fun little name, they're called forests. Similarly, these little important vertices here at the ends, which are only connected to these vertices which are only connected to one edge, called leaves, which is kind of nice. Tree, leaf, forest, very good naming convention. Now, one more type of simple graph I'm going to state here. I'm not going to state the class. It's a class I might look at later. It's a little more complicated, but this example is very important. And any good graph theory course will include this graph many, many times. And you will grow to love this graph for its counterexamples that it provides to many, many features, right? And if you've done a bit of graph theory before, you should know immediately which graph I'm drawing here. Now, I'm going to put our vertices out first. This graph has a vertex set, which I'm going to cheat a little bit and label this way. It has 10 vertices, just like that. Our edges, I will explicitly write out the set first. I'm going to have V1 connected to V2, V2 connected to V3, V3 connected to V4. Let's clean up my handwriting a little bit. I'm going to have V4 connected to V5. I'm going to have V5 connected back to V1. Then I'm going to have V1 connected to V6, V2 connected to V7, V3 to V8, V4 to V9, V5 to V10, and then I have to do 5 more edges, which are the ones which are a little trickier to remember. We have V6 to V8. We also have got V8 to V10. Then we have got V10 to V7. I'm going to do V7 to V9, and I'm going to do V9 to V6. So one notation you'll see, if you're familiar with cardinality, will look like this, where I'm going to say that I have 10 vertices and I have 15 edges in this graph. Now, let's draw it out. How I've labeled this here is I have V1 here, and then I travel clockwise, and that's how I label V2, V3, V4, V5, and then I go in here and I have V6, and then I go clockwise around that inner cycle, and that's V7, V8, V9, V10. Let's join them up. So I have my first 5 edges here, and I'm going to use some coloring. connecting V1 to V2, V2 to V3, V3 to V4, 4 to 5, 5 back to 1. Now, let's consider these 5 edges here. Going to go 1 to 6, 2 to 7, 3 to 8, 4 to 9, 5 to 10. And then, these last ones here, we're going to go 6 to 8, 8 to 10, 10 to 7, 7 to 9, and 9 to 6. Just like that. Now, coloring graphs is an interesting thing that I'll discuss later. For now, these colors are just to help you draw, or help me draw, and you to understand. So I'll clean it up and delete our colors. Let's make those edges, those vertices nice and big again. Now this graph, as you can see, is a simple graph. We have no loops, no directions. It's all nice simple tuples for our edges, so it's not a hypergraph. There is no weightings, and I think I missed one, but that wasn't intentional. As you can see, it is in fact a simple graph. This graph is a Tensor graph. It's KG52. It's also called the Peterson graph. Now, that is your little introduction to various kinds of simple graphs, as well as the definition of a simple graph. Let's go back to our definition. If I go all the way back, and I look at our first graph here. Nice and simple. This is K3. Let's see if we can determine if some other graphs are simple. If I want to draw another graph on 3 vertices, like this, and I do it like this. Is this a simple graph? And the answer is yes. Despite the fact that it's not connected and we have an isolated vertex here, it is still a simple graph. If I was to instead take this graph, right, and actually connect this vertex, obviously, it's once again a simple graph. This one, in fact, is another class of graph I forgot to mention before. It's a path, denoted as P3, just like this. Now, what about some other ones? If I were to take this and I add an edge here and I add another edge just like that, is it still a simple graph? Of course not. Parallel edges. It's now a multigraph. If I was to take one of these away and I was to instead go all the way back to this isolated vertex, you can ask, is this a simple graph? No, of course not. We do not allow loops. Now, the last one, and hopefully you've worked out what the answer is. If I were to connect this back up, and I add an arrow, so now we have a directed edge, it is in fact not a simple graph. Now, this exercise hopefully was relatively simple, and hopefully you've learned a little bit about simple graphs, or you've just been introduced to the topic. There should be more interesting videos uploaded soon, where I'll discuss some other kinds of graphs in more detail, as well as a lot of other interesting questions you can propose when looking at a graph. Thank you.